Hey Algebra 2, this is Mr. Pleasance here. You're watching this video because I've come down with a stomach flu and I was unable to come into work today. But I didn't want us to get a day behind in the calendar, so I made this video. What we're actually learning today is nothing new, really. We're just putting some words to some of the things that we've been doing, and we are also learning a couple different ways to see some of these things. So what is it that we're doing? We're talking about independent and dependent events. So independent and dependent. Think about what the words mean. Well, where do you hear the word independent? You guys remember the song from a couple years ago, INDEPENDENT. Do you know what that means? So you know from the song, an independent woman has her own house, she has her own car, she can do everything, she doesn't depend on anybody. Well, in probability, an independent event is also something that doesn't depend on anything else. So for instance, if we have something like we flip a coin and then we flip another one, it doesn't make a difference what the first one was. If the first one's heads, the second one still has a 50-50 chance of getting heads and a 50-50 chance of getting tails. So it is independent. Now think to our example when we were drawing marbles from our bag. This is where dependent events come in. So for instance, let's say we are drawing marbles from a bag. In the bag there's two blue marbles and a green marble. Well, what's the probability that the first one we choose is going to be blue? Well, the probability is 2 out of 3. So 2 out of 3, which is 0.66. Continue. All right. So if we take out a blue one, what's the probability? Oops. What's the probability if we take out a blue one? All right. So you still got the blue one, and now what's the probability that the blue one the next one will be blue? Well, now it's only a 1 in 2 chance, which is 0.5. So the probability of picking a blue on the second round depends on what we picked on the first round. Building what's called a tree diagram can really help us to see this and understand this better. Alright, so here's our original situation with the bag, 2 blues and a green. We can draw it out with a tree diagram. Okay, so what's the probability of getting a blue? It is 0.66. Continue. And then what's the probability of getting a green in the first round? Well, there's 1 green one out of 3 marbles, so it's a 0.33 chance. Continue. All right, now, given that the first one was blue, the chance of getting another blue, as we determined, was 0.5. But the chances that it would be green after we've picked a blue is also 0.5. All right. Now, what are the chances if we picked a green in the first round here? What are the chances that the second one would be a blue one? Well, it's a 100% chance, so it's a 1 right here. And then the chances that it'll be a green on the second chance, well, there aren't any greens, so it's a 0% chance. So as you can put a 0 here. All right, now this tree diagram can help us to determine the total probabilities for each of these situations. So for instance, if we have a blue, then a blue, the probability is 0.66 times 0.55, or 0.5, I mean, which is 0.33. All right, now the probability of getting first a blue, then a green, is also 0.33 because you multiply 0.66 times 0.5. All right, the probability of getting a green and then a blue is 0.33 times 1, which is 0.33. And then the probability of getting a green and then another green is 0. One thing that you'll notice here is that the probabilities always add up to 100%. Oops. So you've got this. Sorry, I don't know what just happened here. Sorry, I'm not sure what happened here, but my thing just flipped out for no reason. All right, so we figured at the end we had 3 probabilities. We had 0.33, 0.33, and 0.33, and the other one was 0. You'll notice that these always should add up to 1. If you add 0.33333 plus 0.33333 plus 0.33333, since these are all continued, they're all a third, a third, a third, and a third make 1. So an important thing to note, just a little mathematical interesting thing, is these will add up to 0.99999 continued. Well, it's actually the exact same thing as 1, because we know that 1/3 plus 1/3 plus 1/3 makes a whole. Alright, anyway, that's just a side note. So this tree diagram can help us to think about more complex situations too. So again, now we've got this bag. It's got 3 blues and 2 greens. So we can make a tree diagram that says the probability of getting a blue. Oops, I'm going to move this over here. Of getting a blue. And we know that to be 3 out of 5, which is 0.6. And then the probability of getting a green must be 0.4. You'll notice that these probabilities always add up to 100%. Alright, if we pick a blue on the first, this is now called a dependent probability. Don't forget that vocabulary, because it depends on what we choose the first time. Okay, if we choose a blue and then another blue, the probability of that is going to be, well, let's see, if we've chosen a blue, now there's only 4 marbles left, and 2 of them are blue, so it's going to be a 0.5 probability. Which means that the probability of choosing a green is also a 0.5 probability, 50%. Alright, if we've chosen a blue and then another blue, the probability of getting a third blue is going to be, well, if we've chosen a blue, and I can even kind of draw this out for you, if we've chosen a blue and then another blue, now we've only got a 1 in 3 chance of getting a blue. So we'd say this is a 0.3 continued chance, which means again that you've got a 0.66666 continued chance of getting a green. So you can see how this tree diagram can go. And then if you ever want to find what's the probability of getting, for instance, what's the probability of getting a blue, then a blue, then a blue, you would do 0.6 times 0.5 times 0.3 continued, and it'll get you your answer. If you want to find the probability of getting a blue and then a green, you multiply 0.6 times 0.5. So you can use this tree diagram method for anything. And you don't have to make a tree diagram, it's just a helpful tool. So the next thing that I just want to point out here, this is actually pretty self-explanatory, but I want to make it very clear because it might be confusing the way they word it. In the textbook, they're going to talk about, they'll say with replacement and without replacement. That's something that they're going to say all the time. And what they mean when they say with replacement and without replacement is, like, let's say you have a deck of cards. You know, there's 52 cards in a deck. You know, there's ones, twos, or aces, twos, threes, fours, fives, sixes, sevens, eights, nines, tens, jacks, queens, and kings. And there's 4 of each of those cards. So let's say it says, what's the probability of picking a 10? Well, there's 4 tens. So we would say this is pretty easy, 4 out of 52. Okay. What would be then the probability that I would pick, if I picked twice, I would pick 2 tens? Well, it depends on if you replace that 10 that you drew, or if you don't replace the 10 that you drew. So what's the probability that I would draw a 10 if there was no replacement? Well, that's an independent event. Anytime there's a replacement, it's an independent event, because just because I got a 10 on the first round doesn't change my chances of getting a 10 on the second round, as long as we put the card back. So this is going to be another 4 out of 52, so we just multiply 4 out of 52 times 4 out of 52. However, if there isn't replacement, if we take that 10 out and keep it out, it's going to be a different probability. This should seem very familiar. We have a 4 out of 52 chance of getting a 10 in the first try. But if we take out that 10 and keep it out, now there's only 3 10s left in the deck, and there's also only 51 cards left in the deck. This must be a dependent probability, because it depends on what you got in the first round, because we're not replacing the cards. Remember, we said this before, we said this was independent. All right, the very last thing is using a table to find a conditional probability. The way that the book describes this is a lot more complicated than it needs to be, so I'm going to kind of simplify it. So it says, for instance, let's say they said, what's the probability that a carry voter, I'm going to type this out. So it says, first question is, find the probability that a carry voter was from Dallas. Well, you've got to know how many carry voters there were from Dallas. So there's carry voters here, and then there's Dallas. So there's 336 carry voters. And since it says find the probability that a carry voter was from Dallas, then we only need to, the bottom number, the total, just needs to be the total number of carry voters. So we have to add all of these things up. 472 plus 336 plus 207 plus 210 plus 197, and we're going to get our total. And if I did my math right, it's 1,722. So that's going to be our total. So we have 336 over 1722, and technically this is, since it's in thousands, it's 336,101,722,000. But we don't even need to use those numbers, because those thousands cancel out. So we get 336 divided by 1722, and we get 0.195. So that's the probability that a carry voter was from Dallas. So you just have to figure out how many there are in the category, and then what's the total. It says what's the probability that a Tarrant resident voted for Bush, then you'd have to do Tarrant residents who voted for Bush divided by total Tarrant residences. And that's it for today's lesson. Now I want you guys to work on problems number 1 through 14 in the textbook on this chapter. All right, I figured out the page. It's page 815. And I'm going to make a slide that has of it, so that you guys can work off of this or straight from your textbook. All right, so here is the textbook section, and you can just pause the video so that you can see this.